So now let's prove that one. The proof is like this. So I'll just write everything here. Okay, note by triangle inequality, we can actually show that xk delta minus x0 is bounded above by this one minus x star plus x star minus xo. And by assumption, this is less than equal by rho. This is less than equal by rho. So this is less than equal by 2 rho. Okay, so that tells us that xk delta is in this neighborhood. So now, what we need to show is that the error at the kth iteration, at the k plus 1 iteration, must be less than equal the error at the previous iteration k. And to do that, we will need some identity with inner product. So to estimate this one, you need to write something like this one, xk plus 1 delta minus x star. And you need to write this one in this way. So I'll add and subtract xk delta here. Okay, and then by taking the squares here and the square here, and then by computing this with inner products, then by manipulating it accordingly, we will get this one. Square, and then if you subtract by the error at the kth iteration, this will be equal to a term with an inner product. We will just put it here. That's a xk plus 1 delta, xk delta times xk delta minus x star plus the norm of xk plus 1 delta minus xk delta squared. Okay, now we apply the definition of Landweber iteration here. Okay, so we have this one, f prime of xk delta star times y delta minus f of delta. Then you have this one plus, also here we do the same thing, substitute. Okay, and also note that by, of course, this is an adjoint, you can move this on the other side. So we'll have this one, and then we'll have plus, we'll just copy it, this one. Okay, and then from this one, we need to deal with this one by doing this identity here, which can be done by adding and subtracting. Note that term there with the f prime of xk delta times xk delta minus x star. We can substitute it by an identity which looks like this. Delta minus y plus f of x star minus f of x k delta minus f prime of xk delta times x star minus xk delta. We're there. And then plus f of x and delta minus y delta. Okay? Note f of x star is just y. Just We just use it because we want to use the nonlinearity condition. So therefore, we can break this apart further like this. So be careful here because there are lots of terms. Oops, that should be, yeah. I just said to be careful. Delta times, you pair this term here, y plus 2 times xk delta, and then the second group here, okay. And then plus, again, that one. And then this one. And then plus the square there. Square over there. And now, after expanding it, we'll apply Cauchy-Schwarz inequality. So on the first term, that will be less than equal to 2 times this one. Okay. For the second group there in that line, we apply Cauchy-Schwarz and then the nonlinearity condition. So that's from here. Okay, so we have 2 times the norm of y delta minus f of x sub k delta times this one. Note you have eta here from the nonlinearity condition, so let's just put it here. That f of x star minus f of x sub k delta. Okay. And then for the third and the last term, okay, we can just simply rewrite this one in terms of inner products. I mean, inner product. Notice these two here are the same by instead of so we can just flip the sign here, so you have minus 2 times the norm of this one. And also by the scaling term, note this is less than equal to f prime of xk delta square times the norm of y delta minus f of xk delta square. From the scaling condition, this is less than equal to 1, so you're left with plus this one. Okay? And then we can manipulate this further, but first we'll just this one. Now for the first term, we can group it by, can apply the condition on the delta. So we have 2 times for the first term there on the group. This y delta minus y is bounded above by the noise level, same as in the linear problem. Now for the second term, here, we'll apply triangle inequality here. So what we'll do, just imagine adding and subtracting y delta plus y delta. Okay? So we'll have something like this. Times, maybe I'll just put in the other line. Oops. So that's y delta minus f of x star, that's just y, just put y there, plus this one. There. And then simplifying this one, that will be equal to minus y delta minus f of x k delta. Okay? Oh, and then from that one, that's the final form that we need to get. In fact, by regrouping the terms, you can do that. Then we will get something like this. So I'll just put it here. Equals, we can factor out the residual term. Times this one. 2 times 1 plus eta times delta minus 1 minus 2 eta times the norm of y delta minus f of xk delta. Okay? And then there. Okay, now if you look at this one, what we actually want to get is that for this one to be true, we want this entire right-hand side to be less than or equal to 0. Now this norm is, of course, the negative, so we want this factor here to be negative, okay? By using that assertion. And then with that, you can just do it here. Oops. And then from that, we can actually see that that factor there, that 2 times plus eta delta minus 1 minus 2 eta must be less than 0. And then that will lead, by manipulating that one, this will lead you to this sufficient condition. Which I'll just write over here. So that's 2 times 1 plus eta over 1 minus 2 eta delta. Okay. And that completes the proof. And this proof is very important. In fact, this proposition is important. It's also in the reference. And then this result gives us a suitable choice for tau in discrepancy principle. So therefore, we can choose a number tau which is greater than this one. So that means the choice of tau depends on eta. So it depends on the nonlinearity condition. But because in actual applications we cannot know eta here, but luckily we know that this value here for our choice that eta is greater than 1, now we know that this is greater than 2. That means for the discrepancy principle, choosing a number tau greater than 2 should suffice. And then, with that, we can proceed with the other result, which tells us that the discrepancy principle for the nonlinear Landweber iteration is well defined. So, if we let the assumptions of proposition 4.1 hold, and we let k star be chosen according to the discrepancy principle with this tau over here. Note 4.1 is the discrepancy principle, and 4.4 is our choice of tau. Okay? Okay? And this tells us that this inequality holds. And from this inequality, we can show that k star is bounded above by a constant. Therefore, k star must be finite. That means by using discrepancy principle, you must terminate at a finite number of iterations. And also in particular, if we have an exact data, that if y delta is equal to y, then we have this result here, that to infinity, the sum of the residuals must be finite. And this tells us that necessarily, when we apply Landweber method for the exact data, then the sequence of approximates x sub k must converge to a solution of our nonlinear equation. And to prove this one, it's pretty straightforward using the computations that we just performed. So it's like this, okay? Okay, so for that proof, it's like this by using the final form of the proof. In fact, by rewriting that last inequality there, okay? It's less than equal to, by factoring out y delta here, this norm here, so that the other factor will be squared, which is actually what we need, times this one. That will be 2 times 1 plus 8 delta minus 1. Not really. And then by, wait, I think I'm missing something here. What we should get here is that, let me redo that one, okay? But before that, from this result over here, okay, discrepancy principle, this means that also that we can bound delta by 1 over tau times this one, by choosing this value of tau from the discrepancy principle, okay? Okay. So by using this one, we can bound delta there above by this one. So we'll have this one. So we're not square it yet. So 2 times tau inverse 1 plus eta minus 1 minus 2 eta times this one. Okay? And then factoring out y delta, the norm with the y delta here, this will be equal to this one. Yeah, that's the one. Minus 1 minus 2 eta. Right? And now, what we can do is this. We can rewrite this inequality in this way. Okay, and so we have something like this. So we have this constant here, 1 minus 2 eta minus 2 inverse times 1 plus eta times the residual there be less than equal to this one. Okay, and then we let this constant here to be C sub O, and we know that by our choice of tau, we know that this is greater than 0 by our choice of tau over there. Okay, so therefore, if we sum up, say from like this, something, let me just put it like this. If we sum up both the terms in the both sides from k equals 0 to, say, k star minus 1, where k star is chosen by discrepancy principle, then this will be bounded above by x sub o minus x star. Note this is by the right hand side is a telescoping sum, something that we did in the previous lectures. So we have this one. Okay. And from that one, note that in the left-hand side, these are residuals from k equals 0 to k star minus 1. So that's before we use the discrepancy. That's before we satisfy the criterion for the discrepancy principle. So notice that this a residual here inside the summation should be greater than tau delta, okay? Here. So therefore, we apply this bound over here, so we will have something like this. So we have C sub O times tau delta square times the sum of the terms, so that's from 0 to k star minus 1, so that's all in all up to k star, which is what we need actually there. And then less than equal to this one. And then actually to make it simpler, we can actually divide, I'll just put C sub O here, just to be safe. And then this will be bounded above by x sub O minus x star. So we can get rid of this one. Okay? And then by dividing, and then if you continue that, if you divide both sides by C sub O, okay, then you will get that desired result. Okay? And from this one, in the second part of the result over there, this one, this simply tells us that when there is no noise involved, that means if delta is equal to 0, in the limiting sense, the residuals in terms with regards with the iterates given by the Landweber iteration for exact data, they must converge to 0 as k goes to infinity. So in other words, x sub k must converge to a solution of our nonlinear equation over here, right? And then, so we know that the discrepancy principle is well defined. So now we are ready to prove the convergence in the exact case. Okay? And then let's have a look at the proof of this one. So as usual, assuming that the scaling condition and the nonlinearity condition holds, and so assuming that our nonlinear equation problem is solvable with a solution in this this neighborhood here on x sub 0, then the nonlinear Landweber iteration applied to the exact data y, it must converge to a solution of our nonlinear equation. And if we have this abstract condition here about the null space of f prime of x dagger and f prime of x, then x sub k must converge to the x sub 0 minimum norm solution. And let's prove that. Let's see if you can finish that one. Okay. Okay, so oops. So to prove that one, it works like this. Okay, so note in this theorem, we know that x dagger exists. And that's from the previous proposition, the previous result that I cited from the Kaltenbach's paper. So that's here. Okay. Okay. So let's see that x dagger. So we know that x dagger exists. And now by using that same estimates again over there, so it works like this. So we let E sub k be x sub k minus x dagger. And note by the previous proposition, which we just proved, we know that the norm of E sub k is monotonically decreasing. And in fact, it's also convergent because from triangular inequality, we know this one is bounded by x dagger, the norm of x dagger. So it's also bounded. Hence, it converges to some number, let's say epsilon negative. And now, we by that assumption, by that result that we have that these residuals converge to 0 as k goes to infinity, what we'll do is this. So given iteration j greater than equal to k, let's choose an integer L such that, all right, that's between k and j, such that the residual in that iteration is less than equal to the residual at the iterations between k and j. How does it work? It's like this. So suppose, let's try to illustrate that one. So suppose I have k over here, okay, and then, so my j is somewhere, let's say j somewhere here. So if I'm going to, because we know that this is the residual, we know that it converges to 0, so what I want to do is, between k and j, I'll use L so that the residual at this point is smaller than the residuals from here to here and from here to here. So it will look like this. Okay? And I do that for every j. For example, this is j1. For between j2, okay, I'll choose another L between k and j2 so that it's smaller here, and that is guaranteed, okay, because of the previous result that the residuals must converge to 0. Okay? Though it doesn't mean it's monotonically decreasing to 0, that's only for the errors. But for the residuals, it may not be monotonically decreasing, but we know it converges to 0. Okay? So it can, the residual could increase in some way, but in the long run, it must converge to 0. And now we have this nice result. So what we want to show here is that the sequence of iterates is a Cauchy sequence. This is like what we did for the linear Landweber iteration. So it's like this. First, from E sub j, we compute the error, the difference between the errors at E sub j minus ek, and by triangle inequality, this is just, we add and subtract E sub L. Okay, and now, so we want, so our strategy is we want to show that this converges to 0 by showing that these two terms must also converge to 0. Okay, and now by using this one, by using this technique by writing E sub j as E sub L minus E sub L minus E sub j, by inner products again, same as what we did over there, the previous result, we can write that E sub j minus E sub L square is equal to the following. So I'll just write it straight. It can be easily verified. Note, I have E sub L here. There's a reason why. Then plus square, okay? And so the idea is that you just, how do I say that? Take the square of the norms. You can show it, it's easy. And also, in a similar way, we can, so this is related to this one. Also for this one, we can also, by this, a similar technique, we can also show that E sub L minus E sub chi squares equal to this one. E sub k, E sub L plus norm of ek square minus E sub L square. Okay, now let's talk about these two estimates. Because the norms of E sub k converges to some epsilon, so that means these last two terms here, is converge to epsilon minus epsilon, which is 0. Also, this difference here converges to epsilon minus epsilon is 0. So we are left to show that these two inner products must also converge to 0. In particular, let's just show one of them. Just show the first inner product here. This one must converge to 0 as k goes to infinity. This makes sense because of our choice of k. As k goes to infinity, of course, j must also go to infinity. And also L. Okay? And now, to deal with that, we take the inner product of this one. Now note that the inner product, by taking the absolute value, okay? Note E sub L is a fixed, it's an integer that we choose to be fixed in this way, okay? So it is fixed between k and j, okay? And of course, we can shift the sign and keep it like this with E sub j minus EL. Okay? Note L is less than or equal to j. So what we're actually doing is we're actually analyzing the errors here. Okay? Okay? And now, also by using the fact that if you look at this one, E sub j minus E sub L will just be equal to this one. That's equal to E sub, what's this one? E sub j minus E sub j minus 1 by a telescoping sum. That will be just equal to plus E sub L plus 1 minus E sub L. Because this will just be cancelled. Okay? And also more importantly, but later we'll do that. By using that result, we can estimate the following. So we'll just focus on how to use the nonlinearity condition in this case. So from this one, so therefore, by computing the E sub L, this will be equal to the sum, by using the telescoping sum, that will be equal to the sum of E sub I plus 1 minus E sub I times inner product with E L, where I is taken from, so you can see there, it's from L to J minus 1. Okay, and then from that, we can also derive that this one here from our definition of E sub I or E sub k. This is just equal to x sub I plus 1 minus x sub I, and from the definition of the Landweber iteration, this will just be equal to the sum of f prime of x sub I star times y minus f of x sub I times, using the definition of E L, so that's x sub L minus x daga. Okay? Okay, and then note by this is adjoint, similarly, you can also shift this one here. And then by triangle inequality, this will be equal to less than equal to the summation of, so by triangle inequality and Cauchy-Schwarz inequality, this will just be equal to, so I will just put this one here straight away. So just imagine that one, so that I will just have y minus x of x sub I times the norm of f prime of xi times xl minus x dagger. Yeah. Okay. And now we'll use some very tedious computation, which works like this. First, if you look at this one, let's substitute that with the term that we can deal with. Now, what term is it? It's like this. So if I have f prime of xi times xl minus x dagger. Now, note that this term here, by estimating it, will not make sense because you have x sub I here. So you need a term inside with x sub I. So that's this one. Times xl minus x sub I plus xi minus x dagger. Yeah. And then then we can use this result, of course, by the nonlinearity of the differential derivative. We can also add and subtract the following. That's f of x dagger, and then minus f of xi, and then minus f prime of xi times x dagger minus xi. So we group it in this way, and this way. And then from that one, you can also group that with minus y plus f of x sub L. Note this f of x dagger minus y gets cancelled with each other. Since I have f of x sub L here, so that's another group there. And then plus f of xi, so I've subtracted f of xi there, minus f of xl, minus f prime of x sub I times xi minus xl. Note you can be minus there, so I'll just flip the sign over here. Okay. Okay. And now, and this is what makes the linear problems harder to analyze the linear problems. We have. Okay, and now by again applying this, by triangle inequality, we can see that this is less than equal to this one. So by substituting this final term here, and then take the norms, and then by triangle inequality, you'll get this one. Times this one. So first we take the first group. Then plus a second group that's minus y plus f of xl. I'll just flip the sign, so that will be equal to y minus f of x sub L. Okay? And then plus the third group over there, which is this one. So that's the norm of f of xi minus f of xl minus f prime of xi times xi minus xl. Okay? And then you can apply the nonlinearity condition. It's very straightforward. So we'll have something like this. Times this one. So you have eta times xi plus y f x sub L. And also this one here, you can also apply the nonlinearity condition there. And now, by our choice of L, note that also, I forgot to mention that we can apply triangle inequality here, further here. We can add and subtract minus y. So we have this one. And then the x dagger, that's just equal to y, so I'll just put y over there for simplicity. Okay. Then plus y minus f of x sub L plus eta times y minus f of xi. Oops, that should be, okay. Oops, I made a mistake here. That should be I. Okay. Yeah. X sub I, yeah, that should be, yeah. That should be like that, okay? Okay, and then you have that one, that's y minus, no. That should be L, sorry. Sorry about that. L over there. Okay, you have this one. And then also, forgot to mention for that. Note by our choice of L, this is less than equal to the y minus f of xi. So we can replace it in less than equal by the norm of y minus f of xi plus eta times by subtriangle equality, that's minus y minus f of xi plus eta times y minus f of xl. Okay? And again, by our choice of L, this is just y minus f of xi. So by applying that our choice of L, note that everything will be in terms of f of xi, or rather of x sub I. So what will happen is that the final term, I'll just write it here. This will be less than equal to, and by looking at the terms over there, you have eta, eta, and eta. You have 1, so you have 1 plus 3 eta times the summation of square from I from L to j minus 1. And then, by using the result from the previous proposition that this must go to 0 as, what am I trying to show there? As k goes to 0, or rather infinity, okay? And then, from that one, if we go back to the right-hand sides that we've shown, which is just here, oops. So this one goes to 0, so this one also goes to 0, and this one also goes to 0. So that means we are left with a nice result that E sub j minus E sub k goes to 0. And also that's from the fact that from this one, this goes to 0, so both these terms go to 0, go to 0. So therefore here, it goes to 0, goes to 0, so therefore this one goes to 0. And that tells us that by definition, therefore, the sequence of errors, and also in turn, the sequence of iterates is Cauchy. Therefore, by the same remark that we did previously, Cauchy sequences are convergent, so therefore the sequence x sub k must converge to a point x hat where x hat solves the linear equation. Okay? And also, by applying the previous result, by using that additional condition there about the null space, if this is true, of x for all x in is a neighborhood, okay? And note that we know that x sub k is in this neighborhood over here. And then, but the definition, you just let x star be x dagger. Now, because of this one, we can have the following argument. Now, from the definition of the Landweber iteration, we know that xk plus 1 minus xk, because it's in terms of f prime of the iterate, with the adjoint, rather. So that will be, it's contained in the range of f prime of xk star, adjoint. And then from linear algebra, this is contained in the null space of f prime of xk. Then we take the orthogonal composition. the orthogonal complement, and by this assumption here, this is also contained in the null space of f prime of x dagger taken with the orthogonal complement. Okay, and then by using a result by using a previous result from this reference here, you can check this result here that argues that the important possibility in this case is that, in fact, by the same as what we did for linear problems, what this tells us is that x hat must be equal to x dagger. Okay? And also, we can, by using the same result, this is actually, we can also, by using the same procedure as in the linear Landweber iteration, you can also prove the final result that the sequence of regularized solutions must converge to x dagger. And this is theorem 2.6 in the reference, so you can check that one out. Okay, so again, that's about the convergence. Also in the reference, you can also read about the convergence rate. So if you want to go deep in that, in this nonlinear Landweber iteration, you can check that one out. And then that actually ends the lecture. As usual, if you want to learn more about the topic, or if you want any recommendations on this subject, you can feel free to reach me out at my email. So I hope you learned something for the past lectures, and that's it. Thank you so much. Thank you to Simpa for this support, and see you around. Bye bye.